Hello everyone, this is Yifan Yang from the University of Science and Technology of China. Today I will present our paper, Universal Spacetime Stream Backscatter with Ambient Wi-Fi, co-authored with my advisor, Professor Wei Gong. Nowadays, the Internet of Things is widely used to provide various functions. For example, wearable devices and smart homes are common IoT applications. However, with the development of wireless communication, the number of devices and connections has mushroomed in recent years. The huge number of connections enables many applications, but requires a lot of power. As a result, there is a huge and growing energy consumption in real-world IoT applications. To this end, backscatter communication provides a solution. There are many ready-to-use wireless signals in the environment already. Backscatter tags can reflect these ambient signals and embed the tag data onto the signals to communicate with the receiver. Backscatter communication has the cutting edges of low power and low cost, because it just relies on signal reception and reflection rather than generation. These cutting edges are exactly the wishes for IoT devices and applications. Space-time streams are special wireless signals commonly used in Wi-Fi transmitter. Due to the extensive deployment of Wi-Fi devices, space-time streams are everywhere in our lives. There are some prior space-time stream backscatter systems. However, they may have some drawbacks. On the one hand, existing systems apply some changes to the ambient signals. Then they demodulate tag data by finding the differences between the original signal and backscattered signal. In this way, they need two receivers, thus these systems are costly. Not only do they need another receiver, but they also have to keep them on the same page, resulting in more hardware costs and synchronization overhead. On the other hand, existing systems use multiple modulation modes with varied string numbers. Single-stream modulation mode only suitable for single-stream excitation. If we want to leverage multi-stream excitation, the tags should adopt multi-stream modulation mode. However, tags cannot recognize the number of streams of ambient signals independently in a passive way. Since there are different modulation modes in the backscatter tag, they are non-universal. Therefore, they are difficult to deal with real-world ambient signals since the composition of ambient signals is complicated and both single-stream and multi-stream signals exist. Due to these drawbacks, existing systems are kind of inconvenient to use in real-world IoT applications. In this paper, we present ST-scatter to make up for the shortcomings of the existing systems. ST-scatter is a universal space-time stream backscatter with ambient Wi-Fi. ST-scatter is unique in the following three aspects. To begin with, it achieves universal tag data modulation for different types of excitation. Moreover, it only requires the backscattered signals for demodulation, which means only one receiver is required. In addition, it can demodulate tag data and ambient data simultaneously from backscattered signals. To achieve our goals, we need to address the following key challenges. First is how to modulate and demodulate tag data with universal ambient spacetime streams. Prior systems have proposed some methods, but as we mentioned before, they are non-universal. We should come up with a new modulation and demodulation method. Secondly, how to demodulate ambient data from backscatter signals. Existing systems employ another receiver to capture the ambient signal and demodulate ambient data. If we want to obtain the ambient data but don't have another receiver, how can we achieve this? The first step is modulation at the backscatter tag. Basically, spacetime streams are streams of symbols. In spacetime stream Wi-Fi, we choose an OFDM symbol as our modulation unit. The backscatter tag uses RF switches to reflect ambient signals. By changing the control signal of RF switch, we can apply phase shift to different symbols. First, we can employ phase shift keying for tag data modulation. The varying phase shifts across symbols represent the different tag data those symbols convey. We use this modulation method with both single-stream and multi-stream excitation. Now we want to demodulate the tag data from backscattered signals. The phase shift key modulated tag data can be demodulated by estimating the phase shift of symbols in backscattered spacetime streams. Our key insight here is using pilots to estimate those phase shifts. Basically, pilot patterns are predefined in the standard Wi-Fi and are assigned to pilot signals in each symbol. We can estimate those phase shifts as long as we extract pilots and their patterns. However, it is not trivial since we meet three issues. Firstly, how to extract pilots from spacetime streams. Secondly, how do we predict pilot patterns in each spacetime stream? Finally, we find that CPE can be frustrate our modulation. How to remove CPE, then demodulate tag data? To begin with, we should extract pilots from spacetime streams. When the receiver detects the packet, it will convert the received signals to OFDM symbol streams. Then we focus on symbols on separate streams that have the same index. Those symbols suffer the same tag data modulation and thus have the same tag data phase. We extract all the pilots from these symbols. Since the carrier index of pilots is predefined in standard Wi-Fi, our method is feasible. After extracting the pilots, we should find their reference patterns. We figure out the phase shifts by comparing the difference between the received pilots and their reference patterns. However, the pilot pattern changes. It alters in different spacetime streams and changes in different symbols. According to standard Wi-Fi, we predict the pilot patterns in a certain way. First, for each spacetime stream, we have a basic pattern. All pilot patterns are variations of the basic pattern. Second, pilot patterns will rotate cyclically. As soon as the basic pattern is determined, the rotated patterns can be figured out. Moreover, there is a sequence Pn used to control the polarity of the pilots. Pn is fixed and can be produced by the scrambler. The pattern is then finalized once the rotation and the polarity has been determined. After that, we subtract all the pilot phases from the pattern phases. The phase shift can be estimated. Finally, we average all the phase shifts and consider the result to be the final phase shift estimation. However, we find that common phase errors and tag data phases are mixed together in the estimated phases. CPE can be massive, so we have to remove it. Typical Wi-Fi receivers use pilots to remove CPE. However, because pilots now include tag data phases, they cannot be utilized to remove CPE. To this end, we come up with a method. We have an observation that CPE varies linearly with symbol index. Also, the difference between two adjacent symbols is usually tiny. Thus, we exploit this property and come up with the differential demodulation method. For each estimated phase, we just subtract the phase of the previous symbol to remove CPE. Then we get the difference in tag data phase. We use this tag data phase difference to demodulate tag data. We consider the last symbol in the preamble as symbol 0. Then we estimate the phase shift of each symbol. Next, we calculate the tag data phase difference as we mentioned before. Now we can demodulate the tag data. Since we do not apply tag modulation in the preamble, tag data for symbol 0 is 0. We use the tag data of symbol 0 and the tag data phase difference between symbol 0 and symbol 1 to demodulate tag data 1. And likewise, all the follow-up tag data can be demodulated. Now we are thinking about how to demodulate ambient data from backscattered signals. The backscattered signals can be directly used for ambient data demodulation because they are ruined by tag data phases. However, after demodulating tag data, we can easily demodulate ambient data. In tag data demodulation, we obtain the tag data phases. Then we compensate the tag data phases. The compensated signals can be treated as regular signals, which are then demodulated by standard Wi-Fi. Here is the implementation of our scatter systems. The backscatter tag contains a logarithmic envelope detector, a high-speed comparator, a low-power FPGA, and an RF switch. The scatter receiver is prototyped using a commercial off-the-shelf SDR. Now let's see the evaluation. We use single-stream and multi-stream AO2.11n signals for excitation. We also implemented Backscatter with the same hardware prototype for computations. With increasing tag RF distance, we measure the performance of scatter and our baseline Backscatter. First is the tag data BER. The minimum BER of scatter is 0.012% with single-stream excitation and 0.011% with multi-stream excitation, which is 310 times and 472 times better than Backscatter. Then we measure the throughput of tag data. On the one hand, scatter has a much higher tag data throughput than Backscatter. Throughput of around 500 kbps were achieved in our experiments. On the other hand, the throughput of scatter is comparable with different types of streams. However, in Backscatter, the throughput with multi-stream excitation is much lower than with single-stream excitation. Next, we verified the performance of ambient data demodulation. Results show that after our compensation, ambient data can be demodulated with a BER of less than 0.1%. Besides, we conduct simulations to further investigate the performance of scatter with massive MIMO excitation. Results reveal that scatter is universal to support MIMO excitations of up to 8 streams. The tag data BER decreases and the number of excitation streams increases. Here comes the conclusion. In this paper, we present scatter, which is a universal spacetime string backscatter. It achieves identical modulation and demodulation with different spacetime strings. It is able to demodulate ambient data as well. Our extensive experiments reveal that scatter has better performance than Backscatter. Thanks for your listening. If you have any questions, please feel free to drop me a message. You can also check out our PerCom 2022 paper for details.